I actually woke up on time today.
Nice.
First time this semester. I'm so proud of myself.
I'm so proud of you. It only took literally the entire semester.
Yo, I have a startup. It's a startup. It just take care of all your needs. Okay, you're a student, you're an employee. All you like you have to wake up early and show up to work. All it does is just an app on your computer on your desktop that's turn on, logging into BlueJeans, Zoom, Teams, whatever platform you're using, and it just puts a pre-recording background of you like nodding and like agreeing. And if you want to pay the premium price, you're even gonna get an AI narrating your voice and communicating with your colleagues via chat or via verbal if necessary, while you're just chilling there. So, Professor, are you trying to tell us something with your background? Are you trying to escape hell right now?
Uh, the hell is almost over. The course has only one more lecture, and
But the
it'll live
pandemic is here to stay,
happily forever
Professor.
after. We have a visitor, but he's too busy, so he's much more handsome than myself, Professor Ignacio Taboada, but I will impersonate him for this lecture. And it's very pleasant. He has prepared the overheads for us, which are very nice. It's all about experimental point of view. So, his business is sometimes he sits on South Pole. Mostly the graduate students are sent to South Pole. So there is an incredibly expensive experiment going on. They call Ice Cube. And if it's successful, it measures 10 neutrinos per year, but they have to be extra galactic super energetic neutrinos. The physics is totally amazing. And, that's what he does for a living. He's very thoughtful. And because, if you have one event every 12 months, well, no, every month, let's say, if you're lucky, you have to think about your statistics very carefully. Now, the rules, Professor Taboada doesn't like to be disturbed by mere students. So please sketch down the question, write it down, and then after we have gone through Taboada lecture, last week Bart asked, but I said, all errors are the same for purposes of last week. Now, if you're experimentalists, all errors are not the same because there is a curse of systematic errors. And what does it mean? I don't have a ruler at hand, but suppose this is a ruler and I want to measure argon, size of argon. So I stick it on top of argon and I look at it and I say, argon looks like 12.1 centimeter plus or minus 0.1 according to my ruler. But you say, well, have you checked your measurements? So I do it again, and I do it again, and I do it 1,000 times. And, there'll be some statistics in my measurements, but systematic error is that I always get 12 centimeters, even though thing is in angstroms. So that's an example of where you make error measurements, but adding square roots of them doesn't work. If you started adding square roots, it will get better and better, but that's a lie. So that's a systematic error. Now, there might be a better way to say it, but that's how I understand it. I also didn't say what's probability. Probability is a real thing. It's a subject. Now, when you're experimentalist, what you do is you make a measurement. And let's say that, we make n measurements, but r times we get an outcome that we are interested in. Then probability of outcome A is the number of times it shows up as we do our measurement divided by the number of times, limit goes to infinity. So that's called half frequency. How often does it happen? And that's what's available to experiments. Theorists are luckier. Now, in real life, you can't take that limit, so you get an experimental estimate, which we'll call P tilde. Another very important notion is the notion of conditional probability. So in a world of all possible outcomes, there are outcomes called A and outcomes called B. And we might be interested in probability that conditional probability. If we measure A, what's the probability of finding B point in this set? And what it obviously is probability of finding A, which is this area, overlap, intersection, the Venn diagram of A and B. Its ratio is the conditional probability. For example, if I'm rolling dice and I would like to know what's the probability that I get the even roll, so numbers 2, 4, 6, then the probability, there are 6 total probabilities, even ones is half of that, so this is 3 over 6. But probability that I get a number smaller than 3, well, there's only one of those even numbers, that's 1 over 6. So its conditional probability is 1/3. So even though it's, 1/2 to get odd ones, the smaller one than 1/2 of the set, it's a fairly large probability, conditional probability. So now, a very important thing for us is notion of independence. And what all the experiments and all the theory prediction experiments do, they try to reveal correlations. So in Professor Solja's lecture last week, we found out that, what monkey wants to do is its space of, millions of neurons. But in the particular task execution, those neurons are very correlated. So one has to look at modes, at, whole correlated clouds of neurons. But if they're independent, if 2 events happen regardless of each other, then probability of both A and B happening is just the probability of each one happening separately. This is different from worrying about intersection of the sets. Even if they're 0, that doesn't matter. That's different. So that's independent. If A, B are independent, then the conditional probability that we see given A is the usual thing. It's a ratio of intersection of the both sets that both happen, divide the probability that A happens. But because of the factorization, A cancels out. And we find out that probability B, just probability B, doesn't care about, whether A has happened or not, because they're independent. So when we throw dice, if you do it twice, probability of dice being even, given the dice is odd, is the product of this probability dividing by odd. It's just even, so it doesn't matter what the first thing is. Each dice roll is assumed to be independent of the previous one. Out of these considerations comes a very fundamental thing that you will hear a lot if you, curse the internet and you deal with any science in which you have to look at data carefully, and that's a Bayes theorem. The way you derive it, conditional probability A, given that we know that B has happened, is that. Probability that B given A is that. Is, and that just comes the symmetry of the common probability of the two events happening. Doesn't matter which order you do them. So you multiply the sides, you replace, and you find out the two probabilities are related by conditional probability that A happens given B is related to the probability B given A times probability of A happening divided by probability of B happening. So, totally simple, but it's quite important in the way people think about probabilities. So here is an example of applications of Bayes' theorem. Suppose there is an unusual illness which, happens very rarely. So out of 1,000 people, one person gets it. For example, the current statistics in third world country, the leading third world country in the world, that one people out of 1,000 will die from COVID-19, which is a very small probability. There is probability of not dying, which is very high. One person in, my probability is less than 1%, 0.1% that I'll survive. These probabilities can be found by frequentist approach, just by doing measurements, looking at hundreds of thousands of people, millions of people, which are used as database in this brutal experiment carried out by ignorant people. The test is very good because if you apply to 100 people, 98 of them, the sick people, 98 of the sick people will be correctly identified, they'll be positive, and there'll be a probability of 2 of them being misidentified. So that's very good compared to the kind of tests that you should be taking. I'm supposed to be paternal and tell you, please test yourself once a week. The disease is in community. You don't know how you'll get it. You cannot be careful enough. So this is much better test than the one you're taking. So, trivially from this, we have probability that if you get a negative test, you might be positive. But it's only 2% chance. It's very small. And I don't know why this thing exists, not adding up, but I'm not Professor Taboada, so I don't know his secret ways. So if I get a negative test, I'm most likely not sick. So this is all done by clinical trials. There are people who have disease, control group, you do frequentist probability, and that's what you find in your Twitter feed if you follow Twitter. What a doctor really wants to know, if you are diagnosing your patient, you would like to know that if your patient is positive, what's the probability that the test will correctly tell you that? So this is now a conditional probability. It's probability the person is infected and the test, probability the test does it correctly. So according to the Bayes, it's the same as the other way around, divided, divided by these two probabilities. So it's probability that you're diseased and you get positive result, from the sample of people who have it. So this is probability of the diseased. And down there, you have two possible things. You have probability, you have the disease, and you get the test correctly, plus probability you don't have the disease, and you get the test correctly. You put the numbers in, and you find out that probability that you have disease from the positive test is 3%. And you say, well, but my test was much better than that. It turns out when you look at the sample of people, a small number of people who actually have it, then the probability of doing it right is much smaller. In other words, probability of making error is much larger. And the good result in this case is that if you compute also probability of non-disease in this set, you find out that you'll get, rarely. Moving on, but stuff we've done, but now thinking about as experimentalists. So given some data set, we did it as a theory with assumption that we have perfect distribution, and we were computing stuff from probability distributions which are known analytically, etc. They were perfect. In real life, the distributions are just produced empirically. So you do finite number of measurements, you get some average with a bar, which means that's your estimate of average. That itself is a random number that varies. And this week's problem sets and next week's problem sets to do this. Then you can compute the variance. The only thing, the variance has to be unbiased. And again, I urge you to do the problem sets, even though you don't get anything for it except understanding. We have the normalized moments, which I've defined as a theories, but now you do it from data because you're using a mean in the data. The normalized moments are done in units of variance, so they are, basically in units of 1, no matter what you measure. And the important moments are third one, which measures skewness, and fourth one that measures kurtosis. So what are these things? I always keep drawing Gaussians, but it could be that you have a skewed probability distribution. It could be toward right and toward left, and they'll give you negative and positive skewness. And kurtosis says, the two distributions you often use in your life when you are, let's say, doing Monte Carlo simulations or some estimates of statistical probabilities is that instead of using Gaussian, you could use something that's very peaked, saying that I really know this thing much better than just randomly. Or you could use a uniform distribution, which is, so all these curves are normalized to have probability 1 if you integrate over them. But only Gaussian has 0 kurtosis or fourth moment, and kurtosis measures the difference between having a normal, uniform distribution and some very peak distribution. So how far you're from being Gaussian.